My name is A. Ramakrishna, lecturer in ECE, Government Polytechnic Mahbubnagar, and I'll be dealing the subject in third semester, Digital Electronics. And in that, the name of the first chapter is Basics of Digital Electronics. In that, we will see the first topic, which is known as number systems. The main objective of this lecture is, upon completion of this lecture, you will be able to learn or know what is a number system and what are the different types of number systems, and explaining about binary number system, and doing conversion of from binary to decimal, and then vice versa, that is decimal to binary. Next, what is a number system? It is a set of symbols used to express quantities as the basis for counting, comparing amounts, performing calculations, and representing values, and so on. Next, we will see the different types of number systems that are available. The most popular number systems happens to be decimal number system, binary number system, octal number system, hexadecimal number system, and binary coded decimal number system, which you can also call it as BCD. And regarding this number system, we need to study something about base or radix of a number system. The base or radix of a number system is the number of digits that are available in a particular number system. So radix or base of a number system is nothing but the number of digits or numbers available in that particular number system. For example, if you take a decimal number system, the base of decimal number system is 10, because in that decimal number system the digits available will be 10. Similarly, for the case of binary number system, the base or radix will be 2, and for octal it will be 8, and for hexadecimal it will be 16. So that means in decimal number system you will be having 10 distinct digits, and in the case of binary number system you will be having 2 digits, and in the case of octal 8 digits, and in the case of hexadecimal number system you will be having 16 different digits. Next, coming to the first number system, that is decimal number system. So decimal number system uses 10 distinct symbols 0 to 9 to represent different numbers. So decimal number system, as I have told earlier, it has 10 distinct symbols, and those 10 distinct symbols are 0 to 9, starting from 0, 1, 2, and so on up to 9. So these 0 to 9 distinct symbols represents decimal number system. The value of each digit in the number depends in its position in the number. So if you are writing a simple decimal number having 0 to 9 numbers, the value of each digit in the number depends on its position, where it is positioned in that particular number. We will see extension to this. So that's why this decimal number system is also called as positional weighted number system. So since the each digit in the number, the value of each digit in the number depends on its position, where it is positioned or where it is placed, that's why this decimal number system is called positional weighted number system. Next, we will see what do you mean by this positional weighted number system in detail. So if you observe decimal number system, uh, you have this decimal point, and to the left of this decimal point you are calling the numbers as integer numbers, and to the right of this decimal point the numbers you are calling it as fractional numbers. So to the left of this decimal point you will be having integer decimal numbers, to the right of this decimal point you will be having fractional decimal numbers. And the as I have told earlier, the value of digit depends upon the placing of that digit in the number. So if the digit is placed here, that will be having a value of 1. If the digit is placed here, that will be having a value of 10. If the digit is placed here, that will be having a value of 100. If the digit is placed here, that will be having a value of 1000. And if you are moving from the decimal point to the left side, the value of the digit increases, starting from units, tens, hundreds and thousands. Similarly, if you are moving the digit if you are moving from the decimal point to the right side, the value of the digit decreases. So that is, from the right side to the decimal point, it will be 1 by 10th for the first one, and for the second one it will be 1 by 100th, and for the third one it will be 1 by 1000. So the weight of the digit increases 10 times when it moves to the left by one place from the decimal point. Similarly, the weight of the digit decreases by 10 times when it moves to the right by one place from the decimal point. Next, how to represent a number in decimal system. Leftmost digit position has highest weight. As I have told earlier, the leftmost digit, that is MSD, will be having the highest weight, and the rightmost digit, that is LSD, will be having the least weight. So based on this, you can represent the number in a decimal system like this. So MSD stands for most significant digit. It is the leftmost digit is called most significant digit, and the LSD is nothing but rightmost digit. Least significant digit is nothing but the rightmost digit. Next, we can represent the number, decimal number, that is 567, like this. So the analyzation of 567 is like this. It will be, since starting from the decimal point, assuming that 567.00, you can assume like this, so that what will happen, so in the first place you will be having seventh digit, and next 6, and next it will be 5. So it will be 7 into 10 power 0, 6 into 10 to the power of 1, and 5 into 10 square. Okay, so that will be 500 plus 60 plus 7, so that becomes 567. So this is how you are representing the decimal number. Next, we will see something about binary number system. So binary number system is the basis for most of the modern gadgets like calculators, cell phones, digital clocks and whatnot. In today's lives, all these electronic gadgets happens to be the most usable electronic gadgets in today's life. So in almost all in our day-to-day life, we'll be using all these things, in which uh, mostly we'll be using binary number system. Next, and this binary number system is also called as base 2 system, because the radix of this binary number system is 2. That means this binary number system has two distinct symbols, and these two distinct symbols happens to be 0 and 1. So the only two possible digit values for binary number system is 0 and 1. So all binary numbers are represented using binary positional weightage. The abbreviation of bit is nothing but binary digit. And this binary number system can be represented using a digital signal like this. So a low signal represents logic 0, and high signal represents logic 1. Okay, so low signal represents logic 0 and high signal represents logic 1. So this is how a binary number system can be represented with respect to the digital signal. And as I have told earlier, again the same can be shown for the binary number system as well. We have seen for the decimal number system how the numbers are placed. So since binary number system is also a weighted number system, so the position of the bit mainly tells about the value of the digit. And in the case of even binary number system also, you have a binary point, and if you are moving left to that binary point, its value increases, and if you are moving right to that binary point, its value decreases. Since it is also a weighted number system, so whatever the thing that we have discussed for decimal number system, that will be applicable even for this binary number system. And here in the example, this will be most significant bit and this will be least significant bit. In the case of decimal, you are saying it as digit, and in the case of binary, you are saying it as bit. Bit stands for binary digit. Full form of bit is binary digit. Again, here also the positions are 2 to the power of 0, 2 to the power of 1, 2 to 2 square, 2 cube, as we are moving from left from to the left side from the binary point. And in the case of right side, it will be 2 to the power of minus 7, 2 to the power of minus 2, 2 to the power of minus 3, and so on. And so this is the representation of a binary number in binary system. Next, so these are the binary numbers available for corresponding decimal numbers. So for decimal 0, you can represent it with 4 bits, 0 0 0 0, and for decimal 1 it will be 0 0 0 1, and for decimal 2 it will be 0 0 1 0, and for decimal 3 it will be 0 0 1 1, and so on. Likewise, you can have the binary number representation for different decimal numbers starting from 0 to 15. Next, we will see the conversion of binary number to decimal number. First, we will mainly concentrate on integer numbers, whether it is binary or decimal, without fractions. Integer means without fractions. So the steps involved will be: first step, first writing the binary number like this. For example, I have considered 11101 is the binary number to be converted into its corresponding decimal number. So for that, what you need to do, you need to write its binary weights starting from left to right. Right to left. So here, if you are writing the weights, this 1 will be 2 to the power of 0, and this 0 will be 2 to the power of 1, and 2 square, 2 cube, 2 to the power of 4. Likewise, you need to write the weights. After that, likewise, 2 to the power of 0, 2 to the power of 1, 2, 3, and 2 to the power of 4. After that, cross out the weights under zeros. So whenever you are multiplying this with this, what will happen? It will be 0. So resulting will be 0. After that, you need to add the remaining weights. It will be 16. It will be 16 plus 8 plus 4 plus 1, because 2 is multiplied with 0, which results into 0. So the resulting decimal number will be equal to 16 plus 8 plus 4 plus 1, which is equal to 29. So 29 is the corresponding decimal number for a given binary number 11101. Okay, 16 plus 8 plus 4 plus 1, which is equal to 29. So this is the procedure of converting the binary number into its equivalent decimal number. So simply multiplying it with its weights will be converting the binary number into its equivalent decimal number. Next, we will see some exercise examples. 1111. So if you are considering 1111, what it will be? It will be 2 to the power of 0 means 1, plus 2 to the power of 1, that is 2, plus 2 square, that is 4, plus 2 cube, that will be 2 to the power of 3, that will be 8. So it will be 8 plus 4, 12, plus 2 plus 1 will be 15. So for all 4 ones, its corresponding decimal number will be equal to 15. Next, for 100 101. What it will be, if you observe, it will be 2 to the power of 0, it will be 2 to the power of 0, that is 1, plus 2 to the power of 1 into 0, it will become 0, 2 square, that will be 4, plus 2 cube and 2 to the power of 4 will be zeros, and next 2 to the power of 5, that will be 32. So 32 plus 4, 36 plus 1, which is equal to 37, will be the corresponding decimal number for a given binary 100 101. Likewise, you can have a practice of all the binary numbers of conversion. Next, we will see how to convert the opposite, that is decimal to binary conversion. So in the previous slides, we have seen how to convert binary into decimal number. Now we will see how to convert, given a decimal number, we need to convert that decimal number into binary. For that, uh, because since it is much necessary to convert decimal numbers into binary to make computers to accept, because what we think will be in decimal, but what the computer understands will be in binary. So there is a necessity of converting decimal number into binary number. So there are different methods, I think. Double double method. In this method, the decimal number is repeatedly divided by 2 till the quotient becomes 0 with a remainder of 1. So this is one method, which you are calling it as double method. So first, given a decimal number, you keep on divide that decimal number with 2 until what, until where you will be getting the quotient 0 and remainder as 1. So that is the procedure of converting decimal number into binary number. We will see with an example so that you can understand in a better manner. So first I am considering the decimal number 25, for which we need to find out its binary equivalent number. So it will be 25 by 2, remainder will be quotient will be 12, 12 to the 24, and then quotient remainder will be 1, and again you need to divide that 12 by 2, which is 6, and remainder will be 0. And since quotient is not equal to 1, since quotient is not 0, again you need to divide, so it will be 6 by 2, quotient will be 3, and remainder will be 0. Again you need to divide 3 by 2, which you will be getting it as quotient as 1, and remainder is also 1. So the next 1 by 2, which will be getting quotient as 0 and remainder as 1. So the number will be 1 1 0 0 1. Starting from top, bottom to top, you need to count whatever the remainder you got, that you need to write it as a binary number. So binary number will be 1 1 0 0 1. So 25 will be equal to 1 0 0 1 1. So the binary equivalent corresponding to the decimal number 25 will be equal to 1 1 0 0 1. So that will be 1 1 1 0 0 1. So this you need to count it from bottom to top of the remainder, so that you'll be getting its binary equivalent. Next we will see the binary equivalent of decimal 125. Again, same procedure, you need to divide the decimal number 125, keep on dividing the decimal number 125 with 2 until you get the quotient 0 and remainder as 1. And if you are dividing the 125 with 2, it will be 62 quotient and remainder 1. Next 31 quotient and 0 remainder. Next 15 quotient and 1 remainder. Next 7 is quotient and 1 remainder. Next 3 is quotient and 1 remainder. Next 1 is quotient and 1 remainder. So that, and again you are dividing it with 2, so 0 is quotient and 1 remainder. So the corresponding binary number will be this one 1111101. So that will be the binary number corresponding to the decimal 125. So overall summary, what we have seen in this session, we have learned something about decimal number system and binary number system, and as well as conversion from binary number system to decimal, as well as vice versa, that is decimal to binary. In addition to this, we have also seen the some basic terminology like what is a number system, what are the different types of number systems, and what is base or radix of a number system. In the next session, we will be learning about octal and hexadecimal number systems. Next, the number system used in digital systems / computers will be binary. Binary will be the correct answer. Next, decimal equivalent of 110 will be what? It will be, how to calculate? It will be 2 to the power of 0 into 0, that becomes 0, and 2 to the power of 1 into 1, 2, plus 2 to the power of 2 into 1, 4, which is equal to 6. So the answer will be 6. 6 will be the answer. Next, we will see some of the frequently asked questions. You can note it down on your own. So thank you for listening. In continuation to the previous lecture, I will continue the number systems. After completion of this period, you will be able to know what is an octal number and how to convert a decimal number into an octal number and vice versa, and also converting an octal number into binary and vice versa. So in the previous lecture, what we have seen is what is the binary equivalent of decimal number 3. It is 11, and which method do you use to convert a decimal to binary? That is double method. And how many digits are in binary system? That is 2. How many digits are in decimal system? That is 10. So in addition to this, we have also studied something about base or radix. Base or radix of a number system equals the number of digits that number system uses, and the base of decimal number system is 10. It uses the digits 0 to 9, and the binary number system has a base of 2. So coming to the today's lecture, that is octal number system. So octal number system has a base of 8. That means it consists of 8 distinct digits. So it uses the 8 distinct digits as 0, 1, 2, 3, 4, 5, 6 and 7. Next, we will see the conversion from decimal number to octal number. So for this conversion from decimal to octal, we will be using the method called as octal double, which is similar to the procedure that we have adopted in the case of double double method. In the case of double double method, we have used the dividing the decimal number by 2, and in the case of octal double, we should divide the decimal number by 8 until you are getting the quotient as 0. So divide the decimal number repeatedly by 8 until the quotient becomes 0. Write down the reminders after each division, and the reminders should read in reverse order for getting the corresponding octal number for a given decimal number. So if you take an example of decimal number 1, 2, 3, 4, how to convert that into octal? First, you need to keep on dividing that decimal number 1, 2, 3, 4 with 8. So after division of first, it will be 8, and quotient you will be getting 154 with a remainder of 2, and again dividing the 154 with 8, you will be getting 19. Again you will be getting the remainder as 2, and after that dividing 19 with 8, you will be getting 2 as quotient and 3 as remainder. After that again dividing the number 2 with 8, you will be getting the quotient as 0 and remainder as 2. So that the corresponding octal number for a given decimal number 1, 2, 3, 4 will be 2322. So you need to read it from the top to bottom to top, that is 2322. So decimal number 1, 2, 3, 4 equivalent octal number will be 2322. Next, we will see one more example of converting the decimal number into octal equivalent. The number will be now 175. Again, the same procedure, divided with 8. It will be 21 as quotient and 7 as remainder. And again, dividing the 21 with 8, again you will be getting quotient as 2 and remainder as 5. Again dividing, you will be getting the 0 quotient and with remainder of 2. So that the 257 is the corresponding octal number corresponding to the decimal number 175. So this is the procedure of converting decimal number to octal number. And in the previous slides we have seen converting the decimal number into octal number only with respect to integer parts. Now we will see for fractions how we need to convert. With decimal fractions, multiply by 8 instead of divide. So if you are having integers, you need to divide it with 8. If you are having fractions, you need to multiply the decimal number by with 8. And you need to write the carry into integer position so that you will be getting the corresponding octal fraction for a given decimal fraction. So as an example, I am considering the decimal fraction as 0.23, which you need to convert it into its equivalent octal fraction. So first you need to multiply that 0.23 with 8 so that you will be getting 1.84. You need to remove that 1 as carry, and again you need to multiply this 0.84 with 8, you will be getting 6.72. Again you need to remove that carry 6 outside, and again 0.72 you need to multiply it with 8 so that you'll be getting 5.76, and you need to remove that carry with carry as 5. So after 3 or 4 attempts you may get the approximate answer, which is nothing but 165. So 0.165 is the approximate octal equivalent for a given decimal fraction 0.23. So this is the procedure of converting the decimal fractions into its equivalent octal fractions. Now the opposite conversion, that is how to convert the octal number into decimal number. Again, in order to convert the octal number into decimal number, you need to multiply the digits with its corresponding weights, that is 8 power 0, 8 power 1, 8 power 2, 8 power 3 and so on. If it is in the fractional numbers, then you need to multiply it with 8 power minus 1, 8 power minus 2, 8 power minus 3 and so on. So these are the weights. So depending upon the integer part or fractional part, you need to multiply it correspondingly to get the decimal equivalent for a given octal number. To convert from octal to decimal, multiply each octal digit by its weight and add the products. For example, octal 23. So how to convert this octal 23? It will be 2 into 8 power 1 plus 3 into 8 power 0, which is equal to 2 into 8 16 plus 3, which is 19, is the corresponding decimal equivalent for a given octal number 23. Okay, so this is the procedure of converting octal number to decimal number. Next, for fractional part, again you need to have the multiplication with 8 power minus 1, 8 power minus 2, 8 power minus 3 and so on. So given an octal number as octal fraction as 0.28, you need to convert that into decimal fraction. So for that, what you need to do, you need to do multiply 2 with 8 power minus 1 plus multiply 8 with 8 power minus 2, so that you will be getting overall 0.375. So 0.375 is the decimal fraction corresponding to the octal fraction of 0.28. Next, we have seen conversion of octal to decimal and vice versa. Now we will see conversion of octal to binary and vice versa. How to convert given octal number into its equivalent binary and also vice versa. Now first we will see octal to binary conversion. So in the case of octal to binary conversion, first given an octal number, uh, you should replace each octal digit by its equivalent 3-bit binary equivalent. So that is the procedure adopted to convert given octal number into its equivalent binary. So the 3 octal digits and 3 binary equivalents are like this. So for octal digits 0, the 3-bit binary equivalent will be 3 zeros, 0 0 0, and for octal digit 1 it will be 0 0 1, and for octal digit 2 the 3-bit binary equivalent will be 0 1 0. Likewise, for each and every octal digits, the 3-bit binary equivalent is defined specifically. So by following the procedure of replacing the each octal digit with its 3-bit binary equivalent, you can able to convert the given octal number into binary number. As an example, we will see how to convert the octal 736 into binary. 7 means 111, 3 means 11011, and 6 means 110. Simply replacing each octal digits with each octal digit with its equivalent 3-bit binary. Then you will be getting the binary number corresponding to the given octal number. So for 736 octal number, the binary number will be 1110111110 is the equivalent binary for corresponding octal number 736. Next, how to convert the opposite conversion, that is a binary number to octal number. So given a binary number, we need to convert that into octal number. So for that, again the same procedure. The binary number is converted into groups of 3 bits each, starting at binary point. Okay, so by taking the reference as binary point, from that to the left side you are grouping the 3 bits, you are grouping into 3 bits each, and to the right side also you are grouping the bits into 3, so that replacing that 3-bit equivalent with its octal number, then you can able to convert given binary number into octal number. So make groups of 3 bits starting from binary point and moving towards left for integer part and moving towards right for fractional part. Add zeros to the left of integer and right of the fractional part wherever necessary in order to make the group of 3 bits. Replace each group of 3 bits by its octal digit. We will see the example. For example, let us consider the binary number as 1001111.11 is binary number, and we need to convert that into octal. So first you need to divide these binary bits into group of 3 bits. For that, so from binary point you are taking 3 group of 3 bits, that is 111 100, and last bit is 1, and you can append zeros like this, and all in the at the right side also you're having only 2 ones, and you can append 0 to the right side, so that all the bits becomes group of 3 bits, so that you can simply replace the group of 3 bits with its equivalent octal digit. So for 011 the octal digit will be 1, again 1, 7 point, this is 6, so the corresponding octal number will be 117.6. So for a given binary number, the octal equivalent will be 117.6. So this is the procedure of converting binary number to octal number. Next we will see another example of he has given only the fraction 0.10100110. Again you need to divide the binary bits into group of 3 bits, so that you can replace that 3 bits with its equivalent octal digit. It's simple. So it will be 101, which is nothing but 5, 001, which is nothing but 1, and 100, which is nothing but 4. So it will be 0.514 octal. So for a given decimal binary number, 0.514 is the octal number. Binary and decimal equivalents of octal numbers. So here some binary equivalents and decimal equivalents of octal numbers he has given. So decimal 0 means binary 000 and octal is 0. Up to 7 the binary equivalents are same for decimal as well as octal, and for decimal 8 the binary equivalent will be 1000 and octal equivalent will be 10, and for 9 the binary equivalent will be 1001 and octal equivalent will be 11, and for 10 binary equivalent will be 1010 and octal equivalent will be 1. So these are the binary and decimal equivalents for a given octal numbers. Next, we have discussed about octal number system, and we have converted octal numbers into decimal number by using positional weights of 8 power zeros, 8 power 1, 8 power 2 to the left side of octal point, and to the right side 8 power minus 1, 8 power minus 2, 8 power minus 3, and so on. Next, decimal to octal, and we have converted decimal number into octal number by repeatedly dividing the decimal number by 8, and octal to binary, group of 3 binary bits, replacing that group of 3 binary bits with its octal digit. We can convert octal to binary as well as binary to octal. So this is the overall conversions we have discussed till now. Now we will look into the quiz. How many digits are there in an octal system? So the answer will be 8. And what is the base of the number in an octal system? It will be again 8. Next, what is the octal equivalent of decimal 8? So how to convert decimal number to octal equivalent? You need to divide the decimal number with 8, so that, and dividing again with respect to it also 10 will be the octal equivalent corresponding to the decimal number 8. Okay, let us see the options. So option 1 will be correct, 10. Next, what is the decimal equivalent of octal number 12? So how to convert the given octal number into decimal? By multiplying the octal number with its weightages. So that means will be 2 into 8 power 0 plus 1 into 8 power 1, which is nothing but 2 plus 8, which is equal to 10. Okay, so 10 will be the decimal number corresponding to the octal number 12. We will see the options. So option 3 will be correct. Okay, so these are some of the frequently asked questions. You can note it down on your own. Thank you for listening.